Hello students, welcome. Previously, lesson 39, form 3, topic 2, we were dealing with the third, the fourth, and the fifth aim of redox titration. So today, lesson 40, we want to proceed to atomicity and molar gas volume. Let us start with atomicity. We are saying atomicity is the number of atoms in one mole of an element. For example, let us see the table. We have the gas, its chemical symbol or formula, the atomicity of the gas, and terms used to describe the atomicity of the molecule or the gas. So we have helium and neon. Remember, helium and neon were members of the noble gases, and we said noble gases are colorless and monoatomic gases. So that means they were existing in atoms form. So the chemical symbol for helium is He, then neon, Ne, even if we can put there argon, Ar. So their atomicity will be 1, 1, 1 because they are made up of one atom only. So the term used to describe the atomicity of the noble gases will be monoatomic, like helium, neon, and also argon. The term used to describe the atomicity will be monoatomic because they are made up of one atom. So next we are having oxygen, which is written O2. That's the chemical formula for oxygen molecule. Hydrogen, H2. We can put there even chlorine, Cl2. We can put there chlorine, Cl2. We can put there nitrogen gas, N2, like that. Okay, so their atomicity will be 2, 2. Even chlorine will be having an atomicity of 2. Even nitrogen will be having an atomicity of 2 because they are made up of two atoms. For example, oxygen molecule is made up of two atoms of oxygen, so their atomicity will be 2. And the same to hydrogen, nitrogen, and chlorine. So the term used to describe the atomicity of hydrogen molecule, oxygen molecule, nitrogen molecule, chlorine molecule will be diatomic. So next we are going to go to ozone. If you see ozone, it's written O3. That means it's made up of 3 atoms of oxygen. That means its atomicity will be 3. So the term used to describe the atomicity of ozone molecule will be triatomic. Then lastly, we are having phosphorus vapor, which is written B4 as its chemical formula. Its atomicity will be 4 because phosphorus vapor is made up of 4 atoms of phosphorus. So the term used to describe the atomicity of phosphorus molecule will be tetraatomic. Next, we want to proceed to the molar gas volume. Let's go to molar gas volume. So I'm saying molar gas volume is the volume occupied by 1 mole of a gas at a given temperature and pressure. So this given temperature and pressure can be at STB or RTB. So the volume of the molar gas volume or the value in the molar gas volume at STB will be 22.4 decimeter cube. At room temperature pressure, that's RTB, will be 24 centimeter cube. So you can convert this STB, which is in the centimeter cube or in liters, to centimeter cube by multiplying 1000. And you can take RTB, which is 24 centimeter cube, in the centimeter cube to centimeter cube as conversion by multiplying 1000. So let's go to problems involving molar gas volume. I want to start with example number 1. So a total 1.58 decimeter cube of a gas at STB, that's standard temperature pressure, has a mass of 5 grams. Calculate its relative molecular formula. So in bracket, we are given the molar gas volume, M.G.V, at STB, which is 22.4 decimeter cube. So make sure the two are in the same unit, like the molar gas volume is in the centimeter cube and the volume given in the question is in the centimeter cube. So we are saying 1.58 decimeter cube of this gas has a mass of 5 grams. So that means when we are having the molar gas volume, so we ask us, what about the molar gas volume? 22.4 decimeter cube. So what will give us will be the relative molecular mass of the gas. That's what we are going to get. So we cross multiply. So here we are going to have 22.4 multiplied by 5 divided by 1.58. So here we are going to get 71. So the relative molecular mass of the gas will be 71. So in question number 2, we are told calculate the mass of 120 centimeter cube nitrogen gas at RTB, that's the room temperature pressure. Then we are given the molar gas volume at RTB, which is 24 decimeter cube. So here, the two units are not the same. So first of all, we have to make the two units to be the same. So we can have the molar gas volume, M.G.V, which is given 24 decimeter cube to be multiplied by 1000, so that we get 24,000 centimeter cube. That's the first step. After that, let us see first of all, here we are given 120 centimeter cube of the nitrogen gas will be equal to the mass that we are calculating, and the RFM of nitrogen gas will be equal to the molar gas volume at RTB. So let's go and see RFM of nitrogen gas. Nitrogen gas is written like that. So 14 for nitrogen times 2, we are going to get 28. So we are going to say 28 gram will be equal to 24,000 centimeter cube. So we can ask ourselves, what about 120 centimeter cube? So we cross multiply. So here we are going to have 28 times 120 divided by 24,000. So here the mass that we are going to get here will be 0.14 grams of nitrogen gas. That will be how we are going to calculate. So next we are going to go to question 3. We are told determine the volume occupied by 0.2 grams sulfur peroxide gas at STB. That's the standard temperature pressure, and the molar gas volume given there is 22.4 decimeter cube. So here we can say 22, we can say what is the RFM of sulfur peroxide. RFM of sulfur peroxide. Sulfur has a relative atomic mass of 32 plus 16 times 2. That's 64. So you can say if 64 grams can produce 22.4 decimeter cube. So what about 0.2 grams of sulfur peroxide? What volume can it produce? So we are going to say 0.2 multiplied by 22.4 decimeter cube divided by 64. So we want to check what we are going to get using a calculator. So we are going to get 0.07 decimeter cube. So if you're having 0.07, we can convert it to centimeter cube, or you can stop your answer there. So if we want to convert into centimeter cube, we can just take 0.07, then multiply it by 1000. Here we can get 70 centimeter cube. That's how we are going to calculate for that question number 3. We proceed to question number 4. So in question number 4, we are told to calculate the number of moles in 168 centimeter cube of methane gas at STB. Then we are given the molar gas volume at STB to be 22.4 decimeter cube. So this volume is in centimeter cube. We have to make first of all the M.G.V to be in centimeter cube. So we are going to have 22.4 multiplied by 1000. There we are going to get 22,400 centimeter cube. So they're asking us the number of moles. So we can say 1 mole produces the volume at STB, which is 22,400 centimeter cube. So we can say what moles can produce at 168 centimeter cube of that methane gas. So we cross multiply. Here we are going to say 1 times 168 divided by 22,400. So we want to see what we are going to get. We are going to get 0.0075 moles of methane gas. So we go to question number 5. We are told how many molecules are there in 560 centimeter cube of carbon dioxide at STB, the standard temperature pressure. So here, remember we have one big formula. The one big formula that we have is 1 mole of a gas. 1 mole of a gas, or 1 mole, is equal to Avogadro's number of particles, which will be equal to the molar mass. The molar mass of an element or a compound or a molecule, which will be equal to the molar gas volume. So this molar gas volume can be at STB or at RTB. This molecular mass can be RAM if you are dealing with the relative atomic mass of an element, or RFM if you are dealing with a compound, or RMM if you are dealing with a molecule. So this number of particles can be a molecule, or it can be an ion, or it can be an electron, and so on. So here we are told how many molecules are there in 560 centimeter cube of carbon dioxide gas at STB. So if we check here, the molar gas volume at STB will be in centimeter cube, will be STB, it will be 22,400 centimeter cube. That's the STB. So we can say 22,400 centimeter cube will be equal to the Avogadro's number of particles, or the N, which was given in the bracket. So we can say the molar gas volume, which is 22.4 decimeter cube, multiplied by 1,000 for it to be converted into centimeter cube. So we are going to have 22,400 centimeter cube. So we can say 22,400 centimeter cube is equal to the Avogadro's number of molecules. That's 6.0 times 10 power 23 molecules given in the bracket. So we can ask ourselves, what about 560 centimeter cube? What number of molecules can it give us? So we cross multiply. So here we have 560 multiplied by 6.0 times 10 power 23, then divided by 22,400. So if we put this in the calculator, we are going to get 1.5 times 10 power 22 molecules. So that will be the last question for today. Thank you.